Bismillahirrahmanirrahim. So we started talking about the protocols, the difference between international standards and proprietary, and we said that the standards are very important to facilitate the interoperability and the communication between two devices manufactured by different vendors. And the standards, they have to go through phases. First, like call for draft using certain specification for the standard, and then after that, you get some drafts, and then you refine it, and so on. And companies, they compete to get into the standards as fast as possible through implementing some internal prototypes of these protocols, which is what we call them proprietary protocols. So proprietary are not standardized implementation of the protocols, but they are not standardized. And the standard bodies are IEEE and IETF. We started talking about the interaction between these protocols, which is what we called them before protocol suite. So these, we can call all of these as protocol suite. And this example here gives you some how the protocols are interacting together, and it lists the function of one single protocol in every layer in this protocol suite. So for example, HTTP or Hypertext Transfer Protocol, this protocol is responsible for the interaction between a web server and a web client. So this is the first protocol that gets triggered when we say www.google.com. So HTTP protocol takes that request, sends a request to the server, and the server will respond back with the content, which is the content of the page. So the protocol defines the content, how it looks like, the formatting of the request and the response, and how the requests and the responses work. If you send a request with no response, what happens, and so on. The HTTP protocol works on one HTTP client and one HTTP server. So the HTTP server is the one that hosts the web content, and the HTTP client is the one that initiates the communication by requesting this content. Okay, HTTP relies on other protocols to achieve the networking function. So as we can see here, HTTP does not work alone. So it has to interact with TCP, and it has to interact with IP, and so on. The interaction here is not an active interaction, as we will see in a minute. HTTP does not care whether TCP is there or not. The interaction is very indirect in a way that these protocols do not affect each other. In other words, if you use here another protocol other than TCP, HTTP will still work seamlessly. And this is one of the fundamentals of the layered model, which we'll talk about in a second. So TCP is a protocol that's responsible for facilitating the communication between two end applications. Whether this is a client or a server, it doesn't care. So for TCP, any application is just an endpoint. Okay, whether this is a HTTP server, HTTP client, doesn't care. And it needs to send messages. So it gets the message, and then it has to divide it into segments based on certain rules that we will talk about. And then it sends it to the other endpoint. Whether this endpoint is another HTTP or is a FTP or anything. Okay? So TCP is responsible for, first, divide the data into segments, and then perform what we call flow control. So how can I push this into the network? Should I send it like back to back, congest the network, or send them all the way? Or should I send one and then wait for some time and then send another one? This is what we call flow control. It's like you're pouring water into a specific pipe. So if you pour a huge amount of water into it, the pipe will get blocked. You will have some problem. Okay, and no matter how much you push in, what you get out is almost fixed, depending on the size of the pipe, right? So if you push a lot of information back to back very heavily, then you may get all sorts of weird behavior. Like some of these segments will get lost, some of these segments will get stored into somewhere in the network, and it will arrive maybe 1 minute or few seconds after, things like that. You will get some weird behavior. But if you send them regularly using certain rate, which this rate is regulated, then you will get an expected response on the other side. If you pour the water with a rate that the pipe can really carry, then what you will get is what you put. So the rate that you put, you will get it on the other side. Right? So this is what we call a flow control. Reliability talks about the fact that it's reliable in the sense that if you send any segment and it gets lost, you should try to send it again. Okay? And what if it gets lost again? Okay, so that's the responsibility of TCP. TCP guarantees that the segment will get delivered on the other side no matter what, even if you send it infinite number of times. That's TCP. That's how it works. For some applications, this may be a problem. Like for video, okay, if you send the packet, if you spend like a few minutes to send the packet, you better give up and not send it, because if you don't send it, this is 1 pixel on the screen that will not show properly. But if you keep sending it, it doesn't make any sense that you send an information that's obsolete. Like you send it after like 5 minutes or more, and this packet contains information that should be there like 5 minutes ago. So it doesn't make any sense. It's like you're watching a game and there is no synchronization between the video and the voice. It doesn't make sense. So it's better to give up on this packet and lose. So in that case, TCP does not work properly. So in that case, we need other protocols to act in the same level like TCP, which is what we will talk about. So these are the services that TCP provides. So if we get down one level and we talk about IP. IP basically deals with all the endpoints or all the applications as one funnel. So it deals with a host. A host may be running like 100 applications, 100 endpoints, whether some applications can work. You may have on the same machine, on the same host, you may have some clients and some servers, right? Your machine can act as a server for one application, but as a client on another application, right? So again, TCP doesn't care. Each endpoint is independent, and it deals with it as one endpoint. IP doesn't care because it groups all the applications into the host. Any traffic that comes out from a host, IP deals with that traffic as one unit, regardless of which application it's coming from. Okay? And it deals with host-to-host communication. So TCP, application to application communication, okay? HTTP client to server, right? And IP host to host, okay? So IP will be responsible for taking the segments that are divided by TCP, and then it encapsulates them into IP, and through that it stores the source address, the destination address, and then it uses routers to send the packet through the routers so that we can send this packet through the shortest path to the destination. So if we're sending from one host in Qatar to one host in China, we need to get the shortest path between the two machines. Okay? And then, after that, at the end of the day, what we will send actually physically on the medium is analog signal. So who is responsible for sending this data as analog signal on the medium and deals with the medium, whether it's fiber or coaxial? Because if you send it through fiber, then you need to send light. If you send through coaxial, you need to send electrical signal. If you send through wireless, you need electromagnetic waves. So this is the part that deals with converting this data using specific rules into specific physical signals or analog signals that will be sent on different types of media. Okay? And there is a header here because at least in one part of this layer, you still need to chunk this data into specific stream of bits and then perform some error control or again another level of flow control that gets performed here, which we will talk about when we get to this. So this interaction of the network access protocols includes data link and physical layer protocols, and it's responsible for addressing and sending IP packets between two devices. So after we have put the IP address of the source and the final destination, at the end of the day, we need to send it within a local area network. We need to send it to a switch, or we need to send it to the next router. Okay? So, which means that we may actually have to share a medium within a LAN. We need to send through a shared medium. So who will send first? And should we send it to the router directly, or should we send it to a switch first, or something like that? So this is the protocol, or the data link layer protocol is the one that deals with physical devices, physical networking devices. We don't need to send to the router directly. We can send to a switch first, and then from the switch to the router. So it deals with the device-to-device communication, the physical connectivity between a device and a device. Okay? So first, we go, client to server, endpoint to endpoint, and then host to host, and then we break it down into device-to-device communication. So for every hub, there is device-to-device communication. Okay? We'll see that graphically, how it looks. Before that, we need to talk about a very fundamental concept here in networking in general, which is what we call the layer protocols. So this is a fundamental concept in networking, and this is when you talk to anyone, you communicate anything related to networking with any people, you have to talk about which layer you're referring to. Okay? So we have to set some rule, which layer we're talking about here, so that we can communicate. The layered model here, as you can see, the amount of protocols are enormous. We cannot deal with these protocols all as one unit. Okay? So the first thing we should do is that we divide the networking functionality into layers. Here, these protocols are divided into 7 layers. We'll try to simplify it a little bit. As part of this course, we'll simplify it a little bit to talk about only 4 layers. Okay? And the physical layer as well, which makes them 4/5 layers. But this layered model separates the function of the complicated network functionality into parts, structure parts. But there are some very important rules we have to talk about here. So for each layer, we have to define certain information upon which we can use protocols to move this information from one place to another. And then it goes to the next layer, and then it goes to the next layer, and so on. So this layered structure, or this layered models, give us multiple benefits. One of them is that it fosters competition between products from different vendors. We talked about this issue before. As a function, as a startup, I don't have to work on all the network stack all at once. I can be specialized only in transport layer protocols, or I can only invent or develop or design a protocol in the transport layer that provides certain set of services, and that's it. So this makes the competition feasible for many companies, whether it's large-size companies or small-size companies. Okay? And that's a very important issue, because I can keep many companies alive and contributing to this networking stack seamlessly. Okay? The other very strong benefit is that this layered model prevents technology or capability changes in one layer from affecting other layers. This is a very important concept, which is what we have discussed 1 minute ago. If we use HTTP with another protocol other than TCP, it will still work seamlessly. Okay? So TCP deals with data and HTTP as one abstract data unit. It doesn't care whether here there is HTTP or here there is another protocol. It doesn't care. It deals with this data as one abstract unit. Same thing here. And same thing here. This means if I remove this protocol and put another protocol, everything above that will work, everything underneath that will still work. Okay? To facilitate this, all I need to do is just to define this arrow. This is what we call interface. This network interface is very important. And in order to understand this really well, you can think about an interface as, in programming, okay? Think about it as the message header, or the function header. When you declare a new function, okay, or declare a new object or class, you need to define the name of that class or the name of that function and the set of parameters it deals with, right? So this is what we call an interface. You can think about the interface as this is the function header. As long as you send me these parameters and you call this function, I will do the job. Okay? And you don't care what the function body does. Okay? Because the function body will give you an abstract output called data. You don't need to know what's in this data. Okay? So you will get an abstract unit data, and then you put your header and you send it. When you send it down, you need to call a certain function and you give it one abstract data type as a pointer. Send it to the next level. That's it. So as long as we define these interfaces properly, we should have no dependency between these layers on each other, whether in this direction or in this direction. Okay? As long as you call the right function and you give it the abstract data type, it will work. Then, here, you implement your function in any way you see appropriate. So, TCP that's implemented by Microsoft will talk seamlessly and transparently with another TCP implementation that by Apple. The two operating systems, they implement the same. That doesn't mean that the implementation of TCP here is exactly the same. But as long as you define the interfaces properly, you define the function names and the parameters, the abstract types, The body, I don't care. The body will do the job and will give me at the end one outcome. Okay, so that interface is really important. So by dividing into layers and define the interfaces properly, I don't care whether this protocol is implemented by this company or this company, I don't care. So that leaves the room for all the companies to contribute, to innovate, to do whatever they want, okay? And they are not affecting each other. They can still communicate with each other, okay? And as long as they are conforming with certain standards, they can communicate seamlessly without any problems, okay? And then it provides a common language, which is what we talked about now. It provides a common language. As long as you implement the TCP standards, then we'll be able to talk to each other. So we created some common languages. It's like everybody talks English. So we know how to talk English. Everybody talks English. From east or west, we can talk English. So we create this common languages between different heterogeneous and unhomogeneous entities, but they can still talk the same language. So this is by facilitating this layered model with clear definition of all the interfaces. So that's what we need to do. So with that, we have what we call a protocol model. A protocol model, it takes a certain protocol suite, a protocol suite like HTTP, TCP, IP, and a network access layer. And then it creates a model of that protocol suite. And this model maps or matches that protocol suite in a specific model. Okay? And then a reference model is just a generic model that everybody has to follow. The reference model, like we have two reference models here. We have OSI model, or Open System Interconnection model, and we have TCP/IP model. This is the more common one that we will use throughout the course. And as we can see here, this model defines only 4 layers. The OSI model defines 7 layers. Okay? So what happens is that through a specific protocol model, we mapped some of these layers into another, we merged the function of 3 layers here into 1 layer. And those 2 layers have been merged into 1 layer. Okay? So this way we have been able to simplify the protocol model, and we have created a reference model called TCP/IP model, which is the most common model that's used nowadays in the internet. So the internet adopts this model as the most common model it deals with. So that's the reference model. So anything you contribute or anything you develop, you should try to target 1 layer of these 4 layers. Okay? Whether it's an application layer or transport layer or network layer and network access layer. Going back to the standard bodies that we talked about, we said that IETF is one of the standard bodies that deals with internet protocols, and that includes all these 3 layers. Okay? So here, these 3 layers are standardized by Internet Engineering Task Force. Okay? And those 2 layers, this layer, sometimes we break them into 2. Actually, we deal with them as data link and physical layer. This is by IEEE. Okay? So even standard bodies, even those standard bodies, again, the responsibility of the standard bodies is just to coordinate the standardization effort. But the protocols in these layers are just very complicated that it cannot be covered by one single body. So within these protocols, within these layers, there are thousands and thousands of companies that compete and contribute to the implementation of these standards.
So, but not.
Go ahead.
In this structure, the OSI and TCP both reference models. But
Right.
in this structure, we cannot see the protocol model.
The protocol model is just taking the HTTP and all these protocols and to try to create a model that matches this protocol suite. Okay? Usually what happens is the other way around. What happens is that we have a reference model and everybody creates protocols, okay, within that uses one of the layers in this reference model. Protocol model is the other way around. Protocol model is just to take a protocol suite, HTTP, TCP, and so on, and to try to create a model out of this protocol suite. But what happens in real life, what happens naturally, is that you have this reference model, and all the people on the internet, they actually use TCP/IP reference model. Okay, and then you create some protocols, you develop some protocols, or you contribute to the standards of some protocols in one of these layers, which is what we call reference model. So that's the reference model that we're talking about. You had a question? No. Okay. So this is the only place, I think, that we will talk about OSI, because as I said, OSI was the first reference model that was published, but then people started to use more and more TCP/IP model. It's simpler and it matches what happens in reality more. So OSI is you can call it a protocol suite, but I like to call it more accurately like a reference model. A reference model that everybody develops a protocol within that reference model. As we said, OSI lost out to TCP as a protocol suite or as a reference model of the internet. And OSI protocol suite includes layer 3 to layer 7. So from here to here. Because these are the layers that are standardized by IETF. IETF produces all the standards within these layers from IP all the way to any application layer protocol that we will talk about, including DHCP, Telnet, FTP, all these different protocols. So TCP/IP model, or the protocol suite, is an open standard. So this is published. Everybody is agreeing on this TCP/IP model. It's governed by IETF working groups with standard proposed using requests for comments. This is what we talked about before. The first step to producing any protocol is by submitting what we call requests for comments. So IETF will put some calls for new protocols in different layers, and then they get what we call requests for comments. Request for comments, the name is actually very generic, but what happens is that people will send some draft for some protocol specification for the protocols. Here is what we think TCP should work, okay? In details, in big details. This like huge documents, okay? Multiple 100 pages or something. And then it goes to IETF, and then IETF will have like group meeting or something like that. They sit together and they start debating whether we should do it this way or this way, and so on. They have multiple requests for comments, and then they merge on something, and then they release this request for comment as a standard. And then everybody can develop these standardized protocols into their devices. If they do it in the exact same way it's described in the RFCs, then their implementation will be able to work with any other implementation on Earth, even if it's done by other vendors. Okay? We talked about encapsulation before. We said that the process of encapsulation is the process of encapsulation facilitates this loose interaction between the protocols. So it's like you get the content and the header of one protocol, and then you put it as an abstract data unit into another another envelope, and then you send it down, and so on. So this is the process of encapsulation. So, for example, this example here gives you an end-to-end, step-by-step example of how the process works. So first, you have the content from the web page. Then you add to it the HTTP header. HTTP header here will put some information about whether this is a client or the server, what is the URL, this is a request or a response, and so on. And then it will send it. So the next step is that this will go to TCP. TCP will put some information like port number, what is the end, which identifies the endpoint of that application on the host. We'll put some information here and there, and then it will send it to the next layer. IP will put the source IP address, destination IP address, and so on. And then you will have the data link layer header. Data link layer header will send this on the physical medium. So the first thing it does is that it has to identify which next device that this information will go to, whether it's a switch or a router, and so on. So it deals with device-to-device communication. And what happens if there is certain error, and so on. Then it goes through from the server to the client, and then the client will have to, the client here will receive it through the NEC card, and then the NEC card will have to do the reverse operation, which is what we call the decapsulation. So the decapsulation will first extract the data link layer header and trailer, will get the information that it wants from it, and then it will send it up in the stack to the network layer. The network layer will do the same, will extract IP header, process. When I extract the IP header, what I need to do is that I need to confirm that the destination IP address in this packet is my destination IP address, because otherwise I'm not the receiver of this packet. So in that case, either I discard it or I send it to other routers to deliver it. And then it goes to TCP. TCP will do the same, will extract it, and then now if it arrives to the host, to the right host, now I need to put it on the buffer of the right application, right? So it comes to the host as one common funnel, right? But this host has to deliver it to the socket buffer of a specific application. Okay? So TCP/IP is what we deal with in programming as sockets. If some of you are familiar with the concept of socket in programming, if you're not, you will be familiar as part of this course. You will deal with sockets a lot. This is nothing but like a specific buffer that gets assigned to a particular application. Okay? So when the host receives the packet, it needs to put it in the right buffer of the application that it should receive it. Like when you open a browser, this browser will be the client, right? This browser will initiate some socket calls to the internet. So when you receive the content of google.com, for example, you will receive it on the buffer of that browser. Okay? So the host needs to deliver this to the right endpoint, and it goes to HTTP. HTTP will then say, okay, so this is the content that I requested, and this is the response for my request, and so on. So that's the right thing, so it displays the information on the screen. So that's how it goes. So this will have to be done step by step, and this whole thing happens in a matter of sometimes less than a second. Okay? Any questions? So it's left to say that for each layer we have a very important concept called protocol data unit. The protocol data unit is the abstract unit of information that we deal with in a specific layer. So each layer has a protocol data unit. A protocol data unit is in the application layer. The protocol data unit includes the data or the content and HTTP header. In transport layer, the protocol data unit is the data that is coming from the application, which is abstract. We don't know what's inside, and the TCP header. Okay, so this is what we call a protocol data unit. So a very important aspect of defining any protocol on the internet is to define what we call a protocol data unit. What is the header looks like, and what is the actual data? How does it look like in terms of what is the limit of this data? Okay, is it large? Is it small? If there is any limit, what do you do if you get a message which is longer than the limit that you have? Should you put it into chunks or segments, or what do you do, or discard it, or whatever? Okay, so this is the protocol data unit. So in the application layer, the protocol data unit has a specific name. Okay, so in application layer we deal with data. This is a very well-known name. So if I tell you through the writing, this data goes, so all of a sudden you know which level I'm talking about. Okay, so starting from here, starting from this point, we should try to have a unified terminology. Okay, so when you say data, be aware that the person in front of you knows that you're talking about application layer. When you say segment, okay, then we're talking about transport layer. Or we're dealing with TCP. So this creates some again common language or unified language. Okay, so when you talk about packets, network protocol. We talk about frame. We talk about data link layer. Physical layer deals with nothing but bits. That's it, and it deals with bits in the analog domain, not even in the digital domain.
The application seems like they're saying HTTP plus the data, right? And that level of layer.
Right. Yes. So for us, this is data. Okay, because actually HTTP is text-based. Text-based, which means that you have letters. So if you even look at the HTTP header, you will find a readable text. Okay, so for us this is data. When you take it to the transport layer protocol, we call it segment, because this data for us is just ones and zeros, and we just need to add the header to it. So we call it segment, and so on. Okay. So the International Organization for Standards, which is the ISO, this is the one that defined the reference model. So ISO defined OSI. Okay, we don't care so much about that. Just need to know that there is something called reference model or protocol suite or protocol model that defines certain layers for developing these protocols. That's what we need to know. Okay. So that's يعني quick definition about the OSI model, and the OSI model is slightly more complicated than the TCP/IP model, and what it does is that it creates more details in the application layer. So it breaks the application layer into 3 layers. Okay. The TCP/IP model is more logical because I don't care about how you represent the data. You didn't get to the network yet. Starting from transport layer, this is the first layer where you have to deal with networking issues. You need to deliver this information over the network, therefore you need to break it into segments, you need to send it one segment at a time, you need to send it in a specific flow. Before that, you just need to represent your application data into different format of data. But your objective may be to just represent the data and then store it in a file, like MPEG-4. Yani, application creates content, right? Presentation layer is nothing but converting مثلا video into MP4. So maybe you create MP4 to store it locally. You still need to do some presentation. Okay? Same thing with session. The concept of session does not have anything to do with really actual network. So this is session is outside of the networking domain. Starting from the transport layer, this is the actual entry point where you need to deal with the network in terms of you have to divide into segments and send it in a specific flow and so on. So this is the breakdown of application, presentation, and session. So we're not going to talk about a presentation and session layers as part of this course. Okay, so we'll talk about application and then transport, network, data link layer, and physical layer. So these are. So after this part, we will have 5 different chapters. Each chapter will cover one of these layers. Okay, so that's how the course will be structured from now on. Okay, and we'll stop here.